Hi guys, welcome to the lesson of partial differential equation. Now we are going to discuss the problem Laplace equation on a disk, that is also called Drichlet interior problem. Here we can see that we have a disk of radius r, and we are interested to know the temperature distribution in this particular disk inside the disk. So we know that the Laplace equation in the polar form is given by this equation, that is r squared urr plus rur plus u double theta is equals to 0, and uh, r is from 0 to a, given that the boundary condition is u of a comma theta is equals to f of theta. Here on the boundaries the heat distribution is given, and theta is from 0 to 2 pi, and one another condition is that it's ur theta tends to 0 when r is equals to 0, which means that the heat at the temperature at the center is 0, right, when r tends to 0. So now we have the solutions for the Laplace equation, three particular cases: lambda equals 0, lambda greater than 0, and lambda less than 0. So now we can see that from this problem, it's given that r tends to 0 here when ur theta tends to 0, when r tends to 0, right? So when we will plug this r is equals to 0 here, r is equals to 0, so we can say that this will be undefined, so we will have an unbounded solution. But what we need here is we need bounded solution, therefore we don't need this case, right? And again here it's also ln r, and for ln 0 it's again infinite and unbounded, therefore we don't need this one too. So only the solution that we are going to use is this one, right? So now let's apply the periodic and periodic conditions and the boundary conditions to this problem. So since LNR is not defined here, therefore we have a cosine p theta plus b sine p theta times c of 0 power p plus d over 0, right? So now we know that this part cannot be equals to 0 to sustain the solution, otherwise this whole solution will be equals to 0. Therefore we have here we can see that this is already 0. When multiplied by 0, this will become 0, so we will only left with this one, right? So from here we can say that d is equals to 0, which means that now we are only left with the solution a cosine p theta plus b sine p theta times cr power p is equals to ur theta, right? And again we have this we can say that AC is equals to A and BC is equals to B, so we can write a cosine p theta plus b sine p theta times r to the power p is equals to ur comma theta, right? Now we are going to use the periodic condition to find the eigenvalue, that is p, right? So given that periodic condition is ur comma theta is equals to ur comma theta plus 2 pi, as we know in these cases we are using the periodic conditions because it's a circular disk and circular boundary. So here we can apply a cosine p theta plus b sine p theta times r to the power p is equals to a cosine a cos p theta plus 2 pi times b sine p theta plus 2 pi, right? R to the power p and r to the power p cancels out, and now we will arrange the terms. We will simplify. We will arrange the like terms. All right. So now we have the angle identities because we can see here is a cosine p theta minus a cosine p theta plus 2 phi. So here we can see that this is alpha and we can see that this is beta, right? Again, this is alpha here and this is beta. So we can use the angle identities. We have angle identities from trigonometry. Here we can use that. So by using these identities, we finally concluded that 2 sine pi p times a sine p theta plus p pi minus b cosine p theta plus p pi is equals to 0. Therefore, we can say that sine p pi is equals to 0. From here, we can get the eigenvalue that p is equals to n, right? Now we can plug in here in the solution, that is our general solution, So a cosine n theta plus b sine n theta times r to the power n. So now we have this general solution unr comma theta is equals to summation n is equals to 0 to infinite a n cosine n theta plus b n sine n theta r to the power n. Now n starts from 0, therefore we can take a naught outside because here we can see that a naught times cosine 0 will be simply a naught, and we can take it outside, and b naught 0 times sine 0 will be 0, so there is no b naught, right? Now we are left with this equation that is very much familiar, well-known equation, Fourier series, right? So now we can find the Fourier coefficients a naught, a n, and b n easily by integrating the function, by using the properties here. We can see it's 1 over 2 pi. Again, this 2 appears here because we know that in Fourier series here it's 1 over 2, but here it's absent, therefore we multiplied here, right? So it's fine, either you write here or right there, right? So it's 1 over 2 pi, and it's from 0 to 2 pi f of theta d theta. So if we can find a naught from here, then we can find a n from here, and then bn, right? Similarly, so now if the disk is from negative pi to pi, if the conditions are given from negative pi to pi, so it's similar. We will just apply the limits negative pi to pi instead of 0 to pi, right? So we are done with this problem, so we can solve this problem easily if any of the boundary conditions are given. So let's take an example here. We can see that ua theta is equals to f of theta is equals to theta. So now we can simply find these Fourier coefficients to find the particular solution. So we already said that a naught is equals to 1 over 2 pi times the function theta d theta. Right, so here is the integral of the function, which concludes pi, and then a n is equals to 1 over pi times a n into the integral theta times cosine theta. And we will solve this integral. Here we can see that step-by-step solution for this integral, and we applied the limits here. Then we came here, this is 1 over n squared, 1 over n squared, therefore we'll cancel each other, right? So it's b, and now it's equals to 0. So an is equals to 0. Now we will calculate bn, therefore bn is equals to, again, theta times sine and theta. We will solve the integral. This is the integral, and we can solve this integral. So here is the result for this integral step by step, and it's negative 2 over n times an. Therefore we will plug here instead of bn, so we will get the particular solution finally here, right, for the given boundary conditions and periodic conditions. Now similarly for the exterior problem, we are interested in finding heat outside the region, temperature distribution outside this region, this particular region, that is circular disk, outside the boundaries of this disk, right? So for that problem, we know that x squared plus y squared is greater than 0 because we are interested outside the boundaries. And again, this is the equation of circle representing the radius. So this is ur comma theta tends to 0 when r tends to infinity, right? So again, when we are moving away from the boundaries, we will have temperature 0, right? So because we know that the temperature is maximum on the boundaries in the heat equation. So we will move away, when we will move away from the uh, boundaries, or like if radius tends to infinite or radius tends to 0, and then we will have temperature 0. And this is again the boundary condition. So similarly, just the thing that is different in both cases is this r to the power negative n. All other things are similar. So just we are going to use that r to the power negative n in the equation. So here it will be a to the power negative n in the denominator, and here also. That's the difference, and all other things are similar. Right, so in similar manner, we can solve any problem if this condition is given here. Just we have to check that either it's an exterior problem or an interior problem. This one shows that this is an exterior problem, this greater sign. If we have this less than sign, that is x squared plus y squared is less than a squared, then this is an interior problem, right? So you need to identify first which kind of problem is given and you can solve it easily. So let's move to an example. Here an example is given that find the solution of the Laplace equation. Given that Laplace equation in rectangular form, given boundary conditions are in the Cartesian form, it's given that x squared plus y squared is equals to 1 and x squared plus y squared is less than 1, which shows that this is an interior problem, right? This is interior problem and we have radius 1, r is equals to 1, right? From here we can see that. So now we have the solution that you r squared urr plus rur. Now what we are going to do is we are going to solve this problem in the polar coordinates. So first of all, we will convert this equation to the polar coordinates, and we already know the equation in the polar coordinates that is given here. R squared urr plus rur plus u double theta is equals to 0. We know x is equals to r cosine theta, y is equals to r sine theta, r is equals to 1. So we'll plug here. So ur comma theta will be r to the power 4 cosine 4 theta plus r to the power 4 cosine squared theta sine squared theta, right? So we will take cosine squared theta as common, r to the power 4 common. We will left with cosine squared theta plus sine squared theta. Then this is 1, this whole, and we will only left with cosine square theta, which is equals to this one, 1 plus cosine 2 theta plus over 2, right? So u1 comma theta is equals to this function. Now we have the solution for the interior problem in this form. We can just apply the boundary condition which is given, that is equals to this one we already found here, formulated from the given Cartesian coordinate form. Now we can simply compare the coefficients to find the Fourier coefficients, that is a naught, an, and bn, right? So a naught is equals to half. From here, this is the constant we can easily find, and then this series will be equals to half cosine 2 theta, that is a1 cosine theta plus a2 cosine 2 theta dot dot dot. From here we can see that here it's cosine theta, here it's cosine. It means that a2 is equals to half and all other coefficients are 0. And for bn, we already know that nothing is on the right hand side for sine, so all will be 0, therefore all b's are 0. So the solution will be ur comma theta is equals to half plus half times r squared, because at n is equals to 2 we have the solution, so half r squared cosine 2 theta. So this is the final solution. Now we can change it into the Cartesian form, that is x and y. So it's simple, just we need to do here cosine 2 theta is equals to cosine square theta minus sine square theta. So here we can write, and just we can multiply this r squared with both of them, and r cosine theta squared minus r sine theta squared, which means x squared minus y squared. So this is the required Cartesian form for this problem, right? Now let's move to the next problem, and we can see here that now this is an exterior problem. This one shows that this is exterior problem. So we are going to use r to the power negative n here, right? So given ux comma y is equals to 4xy cubed is the boundary condition. Again, r is equals to 1 here. So again, converting to the polar form by using x is equals to r cos theta and y is equals to r sine theta. So ur theta is equals to 4r cosine theta times r square r cubed sine cube theta, right? So we will get this one, 4 cosine theta sine squared theta. Then we have 2 times sine theta, and cos theta is sine 2 theta. Therefore, it will be 2 sine 2 theta. Here's 4 times this sine squared theta is 1 minus cosine 2 theta over 2. So we have sine 2 theta times 1 minus cosine 2 theta, which is equals to sine 2 theta minus sine 2 theta cosine 2 theta, which will be this one, right? Because again we have 2 sine 2 theta cosine 2 theta is equals to sine 4 theta, right? It's already written here. So it will be sine 2 theta minus half sine 4 theta. Again, we are going to apply the condition to the general solution. This is the general solution here, r to the power negative n because of the exterior problem. And then we will compare the coefficients again. For a naught, we have nothing on the right hand side, so a naught is 0. Again, for an, we have nothing in terms of cosine on the right hand side, so an is 0. Only what we are going to get is bn, and bn for what? For n is equals to 2 from here, and n is equals to 4, right? So we can see that b1 is equals to 1 and b4 is equals to negative half, right? So it's simple. Now we can construct the final solution. So it will be equals to ur comma theta r to the power negative 2 times sine 2 theta. Remember that we have r to the power negative n in the solution. So it's n is equals to 2 here, therefore r to the power negative 2, and here it's n is equals to 4. That's why it's r to the power negative 4 over 2. So this is the general form. Now we are going to convert back to the Cartesian form, a rectangular form. So what we did here, we simply divided and multiplied by r square because it's sine 2 theta, and we are going to get a squared form of angle identity, right? Either cosine or sine. And here we multiplied and divided by r to the power 4 because here is sine 4 theta, and we are going to get in the power 4, right? So now we can write it here like this: 2r squared sine theta cosine theta, because sine 2 theta is equals to 2 sine theta cosine theta, right? And here's sine 4 theta, therefore we are writing or we can just simply write 2 sine 2 theta cosine 2 theta. Here we can see that, right? So further simplifying this problem, now it's 2r sine theta and r cos theta, therefore it means 2 into y into x, therefore it's 2xy, and r squared is equals to a square root of r squared is equals to x squared plus y squared. We already know that, x squared plus y squared. So we can simply write here x squared plus y squared whole squared, and for here it's sine 2 theta cosine 2 theta. We can split sine 2 theta into 2 sine theta cos theta, and cosine 2 theta is now equals to cosine squared theta minus sine squared theta, right? So we have now sine theta cosine cube theta and sine cube theta cosine theta. We will multiply this r power 4 here. So this will be r4 times this. Sine theta cosine cube theta means this sine theta, r times sine theta will be y, and r cube times cosine cube theta will be x cube. And similarly here, r cube times sine cube theta is y cube, and r times x cos theta is x, right? So now we have the final solution in the form 2xy over x squared plus y squared power 2 and this function, right? So again, we have the final particular solution of the form, and we have converted to the Cartesian form. So you can see that we can easily solve the problem by converting it from the Cartesian coordinate system to the polar coordinate system. So hope you guys will learn from this lesson. Thanks for watching the lesson, and that's all for the time being. Thank you. Goodbye.